Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have discussed the Gram-Smith orthogonal process and the QR factorization. Now, today we are going to generalize the concept of dot product and we are going to introduce the inner product space. So, let us do that one. So, as in the previous lecture we have discussed that if we have a set of linearly independent vectors, then with the help of Gram-Smith process we can make them orthogonal and then normalized. So, we can make them orthonormal set of vectors, and using that vectors we are able to factorize the given matrix A into the QR form. So, that is the Q is that the corresponding orthogonal matrix and this is the upper triangular matrix. So, that we have discussed in the previous lecture, and in this case we just want to say that it may happen sometime that this QR factorization. So, whatever we are doing here, I can write here that if the matrix A that is n cross R in the QR factorization, then also we can have a that is n cross R. So, this can be written as a q that is also n cross R, because A will contain the vector R vectors each of dimension this. So, in this case we have a V is, suppose we are dealing with R n, and then I take the set, a set containing V 1, V 2, V r. So, it is basically it is a basis of some subspace of R n. So, based on this one we will convert this one into the orthogonal set of vectors we represent by u. So, here we are representing by u. So, this is my basis, and then I will convert this one into orthonormal vectors, with the help of Gram-Smith process. Then it will be A will be of n cross R, where A is the matrix corresponding to the, putting this vector as a column vector, this will be n cross R, and then R will be R cross R. So, this matrix we are writing here, this is always upper triangular. Matrix, because their dimension, this is a rectangular matrix, this is a rectangular matrix, but this will be a square matrix and this will be a upper triangular matrix. So, QR factorization is also possible when we are dealing with the basis which is a basis of a subspace instead of the complete vector space. Now, after doing this one, today we are going to discuss about the inner product space. So, we have discussed that whenever we take the Gram-Smith process, we deal with the dot product. So, that we know that this is what we have used for the vectors. Suppose we have a vector maybe u1 and u2 belongs to some vector space R n, then we have defined u1 dot u2. So, that is the dot product of dot product, because using this dot product only we are able to tell whether these vectors are going to be orthogonal or not. Now, suppose we take vector space of all the matrix of order R cross R. So, it is also a vector space, it is a vector space. Then suppose I take the matrix A and B belongs to this vector space, then how we can say that A and B are orthogonal? How we can say that? Or maybe I will take a set of polynomials. If I suppose I take the Pn define over a interval a b. So, it is a set of all polynomial of degree less than or equal to n, and x belongs to the interval suppose a b. So, in this case also suppose I have a polynomial p and q that belongs to p n, then how can we say, how we can claim that p and q is orthogonal? Or suppose I take the function f x and maybe f x and g x that belongs to the vector space of all the continuous function defined from a to b. So, in this case also I want to check that f x and g x are orthogonal. So, how I will check? Because we do not know that how to take the dot product in this case. So, to define this type of things, we do the generalization of the dot product, and then we define the generalization and we call it inner product space. So, you can say that here that this is generalization of dot product. So, what is this one? So, let us write the formal definition, because in this case, so we call it that an inner product on a real vector space. So, we are talking about here real vector space V is a function. So, is a function that associates a real number. So, we represent by this one. Suppose I take a u and v from the vector space V, then we represent this inner product by this way. So, by the real number this one with each pair of vectors, in V in such a way that the following axioms are satisfied. For all vectors u and v belongs to the vector space V, and all scalars k. So, it means that we are defining a function that is going from V cross V into set of real numbers. So, this is called the inner product. If it satisfies the following axioms. So, first, what is the first axiom? So, first axiom is that if I take u and taking its inner product with itself, then this is always greater than or equal to 0. So, it should be always positive, and if u with u itself is 0, that implies that u should be 0. So, this is called positivity axiom. The second one is that if I have a inner product with u and v, and if I change this to vu, then its value should be same, and this is called symmetric property. Third one is we have, suppose u plus v and w is some other vector, then it should be equal to uw plus inner product vw, and this is true for all u, v and w. So, this is called the additive property. And the fourth one is suppose I have a scalar k, u and v, then I am taking the inner product, then it should be equal to, I should be able to take the k common, and then I should be equal to v. So, if this is true, so I can write here from this is true for all u, v and w belongs to the vector space V. This is also true for all vector spaces where k is a scalar. So, in this case, if all these four properties are satisfied, then we say that whatever we are defining here is an inner product, and so from here I can write that, so a real vector space with inner product. So, I can say that with an inner product is called inner product space. So, here we are talking about real. So, it is called the inner product space, or maybe I can write here real, because we are talking about real. So, real inner product space. So, these things we just change the name and then we are able to do that. So, all these properties is to be satisfied. Now, you can verify this. So, we can verify that standard dot product, or I can say that the standard inner product that is equal to dot product satisfy all the axioms. So, if we call it the standard inner product, it means we are talking about the dot product we have discussed about the vectors in Rn. So, that is called the basically standard inner product, or we also have a some other type of name. So, this is also called Euclidean inner product. So, Euclidean means we are talking about the Euclidean geometry. So, in that case we take the dot product inner product as a dot product. So, that is also called the Euclidean inner product. The standard inner product or the dot product or the Euclidean inner product all are same. Now, from here if you see whatever we have defined u dot product u, I can write as u u. So, we are defining this inner product as a dot product, and these things we already know that this is equal to u magnitude square, or we also sometimes write like this one square. So, whenever put this line, then we call it norm. So, norm of the vector is also here in this case is also associated with the inner product. So, this is satisfied, that is always positive, or if it is 0 then this value will be 0, that is also symmetric. This is additive, or maybe I can call it distributive, and fourth property. So, all the properties we can verify that this is satisfied by the standard inner product or the dot product. So, now we will discuss about the inner products in other vector spaces. Now, we can discuss, after discussing this one, we can discuss weighted Euclidean inner product. So, Euclidean inner product is same as a dot product, but here we are defining the weighted inner product. So, suppose we have, so we vector space is, suppose this is R n, so it is a Euclidean space. Then in this case I take, suppose I take a u belongs to V. So, my u is basically, I can write it as x1, x2, xn, or maybe I will take it as a x. Then I define another vector y, that is y1, y2, yn. So, it is belongs to V, it is also belongs to the given vector space V. Then we define a vector that is w1, w2, wn, that also belongs to V, such that each Vi is positive. So, this Wi is we represent as a weight. Then we can define the weighted Euclidean inner product. So, we represent by this one. So, we are writing inner product x y. So, this one is basically we are representing by, if we take the normal dot product, then it is equal to x I into y I, then we multiply by w I, and I is from 1 to n. So, in this case we have taken the this dot product multiply by w I. So, this is, if we take this one, this is called the weighted inner product or weighted dot product. For example, suppose we have some random variable, like suppose I have a x, that is a random variable, and it has the value x1, x2, xn, some data is given to me, and suppose I have the frequency of each x. So, it is f1, f2, fn. Then we know that the arithmetic mean, if I want to take, then the arithmetic mean of x. So, this is we write by taking x1 f1 plus x2 f2 xn fn divided by the total frequencies and suppose this is equal to n. So, from here I can write this as 1 over n x1 f1 x2 f2 xn fn. Now, from here you can see that this is can be written as dot product of x with frequencies divided by n. So, in this case I can say that the weight function weights. So, I can represent here the weights Wi in this case is 1 by n. Okay, so, from here that we can find out the arithmetic mean with the help of taking the weights, that is 1 by n in this case. So, this is a weighted dot product we take in the case of a data, whenever we have a data and this is the frequencies, and this is my some data, numerical data. Then I want to find out the mean, then we apply this formula to find out the arithmetic mean. So, this is one of the way to find this one. Now, so after doing this one, I will want to find about the inner product in the space of matrices. So, let us define the inner product in vector space of matrices M of order R cross R. Suppose I take for example, I take M 2 by 2. So, I just take 2 by 2. Suppose I take the matrix A, I will write like this one 1 0 maybe 1 1. I take another matrix B, that is 2 1 0 1, something like this one. Now, I want to say that this matrices A and B are orthogonal to each other, or I want to take the inner product of A and B. So, how we can define? So, I want to define this one A and B inner product. So, this one I want to define that. Okay, so, and if we define an inner product, then it should satisfy all these 4 conditions, then only we say that the inner product is well defined. So, in this case how we define is, let us take the definition. So, what I do is that I define A, B, the inner product. I take it as, because if you know, then the dot product here, whatever we have defined this one, this dot product can also be written as U transpose U, because whenever we take U as in the matrix form, then we know that U is a column. So, U transpose become the row vector and multiply by U. So, it is a matrix multiplication. Matrix multiplication. So, now I know that these matrices are also made up of vectors. So, I take the idea from here and then I define inner product here as, I will take the trace of A transpose B. So, this one I am defining, and we know that the trace of a matrix is basically sum of diagonal elements, sum of main diagonal elements. So, I am defining the inner product in this way. So, for example, let us take this matrix and I want to define the inner product of A and B. So, in this case I will take inner product of A and B. So, I will take the trace of a matrix. So, this is the matrix we are going to define. So, A transpose will be 1 0 1 1, I am taking the transpose, multiply by B, that is 2 1 0 1, this one. Okay, so, from here now this will be equal to, I want to take the trace of the matrix. So, I just multiply, so it will be 2 0, so it will be 0 1 1, it will be 2, because 1 into 1 and 1 and 2, and this is 1, and this is the resultant matrix. I am taking the trace. So, trace is 3, that is 2 plus 1. So, I am getting the value 3. So, from here we found that the inner product of these two matrices is equal to 3. Now, the question is that whether it is satisfying this all the fold condition or not. So, that we need to find out. So, verification, that verify. So, this verification we can do. One thing I want to see from here, that let us see what will happen to when I am taking the inner product of A with itself. Then I can take from here, this is, I will defining trace of A transpose A, and if you take a matrix, any matrix, suppose I take the matrix A as A 1 1, A 1 2, A 2 1, A 2 2, and I take A transpose A, then if you see from here, it will be A 1 1, A 1 2, A 2 1, A 2 2, and this is A 1 1, A 1 2, A 2 1, A 2 2, and from here I can multiply. So, it will be A 1 1 and A 2 1. So, it is my A 1 1 square plus A 2 1 square, this one. Now, from here I will get A 1 1, A 1 2 plus A 2 1, A 2 2. Then again I am getting A 1 1, A 1 2 plus A 2 1, A 2 2, and the last one it will be A 1 2 whole square plus A 2 2 whole square. And then if I take the trace of A transpose A, then it will be A 1 1 square plus A, I can write from here. So, I can write A 1 2 square plus A 2 1 square plus A 2 2 square. It means I am just taking the trace. So, this plus this. So, I am putting all this together. So, if you see from here, then this is equal to taking the square of each and every element of the matrix A. So, that is going to be the trace of this one. So, I am using this one here. So, from here then it should be equal to, and always you can see from here that it is taking the square. So, it is always greater than equal to 0, unless until all the element at 0, it is always greater than 0. So, it is always positive. So, from here I can say that the trace of A will be 1 1 1. So, it will be 3 in this case, because I am taking this square plus this square plus this square. So, it is 1. So, no problem. Or maybe I can take trace or the inner product of B with itself, that is trace of B transpose B. So, this will be 4 plus 5 plus 6. So, it is equal to 6. and this is positive, that we know. Also we know that if I take the norm of A here, so this will be taking the inner product of itself by the square root. So from here this will be equal to under root 3. Similarly, I can define the norm, or we used to call in this case the length. So this is we used to define. So from here you know that the length is always taking the square root. So this is always I am taking B. So this is under root 6. So first property is satisfied of this one, that this is always positive, and whenever it is 0, so whenever it is 0, if this is equal to 0, it means all the values of the matrix will be 0. So that property is satisfied. So I can say from here properties or axioms to be satisfied. So first one is I am taking that A with this is always positive, and if this is inner product is 0, which implies that A is 0. So that is true, that all the elements should be 0. Second one is that, second one we want the symmetry. So we know that we are defining by A B. So here we have defined A B as trace of A transpose B. Now I want to see that what will happen if I take it B A. So B A should be trace of B transpose A, and if you see from here, then I know that A transpose A transpose B is always equal to B transpose A transpose transpose, that is B transpose A. So if I take the transpose of this one, then I am getting this value. And we also know that the trace is just the matter of the elements at the diagonal, and we take the transpose, then the diagonal element is not going to change. So we also know that the trace of some matrix A transpose is always equal to trace of A, that we always know. So from here we can say that trace of A transpose B is same as trace B transpose A. So from here I can say that this is equal to B A for all matrices A and B belongs to the space. So this is I am taking any matrix of order R cross R. So third one is also. So now from here I know that one more thing, that suppose we have two matrices, let we take matrices A, B, C belongs to R cross R, then I want to take A, B and C in a product, then this will be equal to the trace of A plus B transpose C. So this one we can define, and this is equal to trace of A transpose B transpose C, and this can be written as, so I can define from here trace will be A transpose C plus B transpose C, So, I am just taking two matrices and adding, then I am finding the trace, then it is same as I am taking the trace of A transpose C plus trace of B transpose C. So, from here you can say that for any two matrices A plus B C, that is equal to A C plus B C. So, this is true for all A, B, C belongs to the vector space of the matrix R cross R. And the fourth one is I take any scalar k. So, it is very easily we can say that we just take the k common, then I can write this as inner product of this one, for k belongs to the real line. So, it is here it is a scalar. So, I am taking the real vector space. So, it is a real number. So, all these four properties are satisfied, and from there we can say that this inner product defined on, so inner product, so this is equal to trace of A transpose B is an inner product defined on a vector space of matrices M of order R cross R. So, this is the inner product I can define on these matrices. Now, this once we define this inner product on the matrices, then we can talk about orthogonality. So, using this inner product, we can talk about orthogonality. So, how we can say, let I take the matrix, some matrix I just take U, I just take the matrix 1 0 1 1, let us take this one, and I take another matrix, I just take it 0 2 0 0. Suppose I take this matrix and I want to check that whether these two matrices are orthogonal or not. So, check whether U and V are orthogonal. So, this one we want to check. So, what do we do? I will take the inner product. So, in the taking the inner product, I will take the trace of the matrix. So, U transpose is, it will be 1 0 1 1 and V will be 0 2 0 0. Suppose I take this one and then I will take the trace. So, it will be 0 and then it will be 2. See, I am taking this value with this 0, this value with this is 0, this value I am taking with the here it is 2 and this value I am taking here is 0. So, its trace will be 0. So, from here I can say that the inner product in this case is coming 0, which implies that U and V, the matrices, are orthogonal to each other. Now, suppose I want to normalize this matrix. So, these are orthogonal to each other. Now, let us normalize this one. So, how to normalize? So, by normalizing the matrix U. So, how we can do the normalization? First of all, I want to find normalization here. So, that will be equal to U divided by its norm or its length. So, this one I can write. Now, U is 1 0 1 1, and this one I know that this is equal to taking the dot inner product and the square root. So, this is, we already found that this is equal to under root, and this is the square of all the elements of the given matrix. So, it was 1 plus 1 plus 1. So, it is under root 3. So, I can divide by under root 3. So, from here I will get this matrix. So, normalized matrix U is 1 by root 3, and then I am taking 1 0 1 1. So, this is the way we are able to do this normalization. So, now if you can, from here you can see that if you take its norm, then it will be equal to 1. So, this way we are able to find that how we can define two matrices orthogonal to each other and how we can normalize this one. So, we will stop here. So, in the today's lecture we have introduced the generalization of the dot product, that is the inner product, and then we have defined that how we can define the inner product on the vector space of matrices, and we have shown that how we can say that two matrices are orthogonal to each other. So, in the next lecture also we will continue with this one. So, thanks for watching, thanks very much.